Well, it's another great day to be you, and today you are going to learn about Taylor and Maclaurin series. So first of all, to talk about this, so you can't really talk about Taylor and Maclaurin series if you don't know what a power series is. So I've spent other videos discussing this. I would say that you should have some homework on this under your belt before you start this video, because you do want to have a general sense of kind of how the power series works. So now let's talk about how do we get to a Taylor series. So what we're going to do is we're going to take our power series and we're just going to start looking at term by term differentiation. So this is my power series just kind of written out in its term by term form without the summation notation. And so a challenge to you would be, if you take the first derivative, what does this look like? So maybe pause here and give that a try. So if I take the first derivative, so here, this x drops out, right? This is just x to the first. This a is just a constant, so all of this drops out, and I'm just left with a sub 1. And then this term here, so the 2 will come out in front, and then I've got x minus a to the first, and then we can continue this pattern. So this had a 3 here, so now the 3 comes down, so on and so forth. So now moving on to the next derivative. So this was the constant term, so as you can see, it's fallen out. And now this term is going to become the constant because this is just to the first power, so the x will fall out. And it just kind of keeps going, right? So now this term, we're going to bring that 2 down. So now I have 2 times 3 times a sub 3, x minus a. And then this was 3 times 4 times x minus a sub 4, x minus a to the second. And if we continue this on to the next derivative, so then this drops out. This becomes the new constant term, and the pattern really just continues. And so the question really here is, what is the pattern? Can you summarize it? So that would really be our next step. So I don't necessarily expect this perfect formula, but what I want you to do, just to check in with yourself on how you're understanding this, is I want you to look at all of this and say, how could you simply describe the pattern here? Pause here, just write down a thought or two about that before I tell you. So hit play when you're ready. So you can kind of see that we have this almost like factorial pattern going here, right? So I have the highest term and then the next and then the next. So there is some sort of pattern here where it's like n factorial times some term a sub n, and then you have some other terms, right? So if you look at this first term, right, this is kind of going in that n factorial way times whatever term we're on. So I'm sure we could refine this pattern much more, but this is really good enough for what we need. So now what I want to do is I want to take a second to evaluate all of this at the value x equals a. So where I have this f of x, I'm now going to replace this f of a. So just think about this for a second. If you plug in x equals a, what's going to happen? So looking at all of these terms here, if I plug in x equals a, this will be a minus a, so this all just becomes, this is all going to be a bunch of zeros. So all of this stuff here, these are all going to turn into 0. So to summarize that, if I plug in a into everything that we see here, so this is how we could kind of formalize everything, right? So just that first term, plugging in x equals a. Okay, and now from here, we're almost to the definition of a Taylor series. So what I'm really interested in is having some better way to maybe describe the coefficients that go with my power series. So what I'm talking about is I'd like to have a more general formula for this a sub nth term, right, which is the most general term possible. So I can actually pretty easily solve for this now that I see this pattern that's been established. So if I solve for this, I can just see that my a sub n will equal the nth derivative of a over n factorial. So, okay, this is kind of now a weird thing, I guess, that where we've inexplicably, in some way, right, we ended up finding a way to solve for these coefficients that seem like, oh, they're just random whatevers, and now they're not, right? It's like, oh, there's actually a formula for these, as long as x equals a. Okay, so we've got all that. let's go back to the power series and put all this together. So where I started, right, was I had this is what we were talking about. This was my like general power series. And so now what I'm telling you is that I actually have this formula for each one of these a sub whatever terms. So I can use now this a sub n equals the nth derivative of a over n, oh, that should say n factorial. Let me put that factorial in my bed, n factorial. Okay, so, okay, cool. So let's do that. So let's see what we get. So what I'm going to do now is I'm just going to go through. So for each of these, I'm now going to replace with the formula that I have. So my a sub 0 then would just be f of a. My a sub 1 by that formula should be f prime of a. My a sub 2 is going to be f double prime of a over 2 factorial. And then we can just continue this pattern. So the a sub n will be the nth derivative of a divided by n factorial, so on and so forth. Okay, so this is another way now that we can state this. And all right, finally, I can tell you this is what a Taylor series is. And so Taylor series, it's kind of this big thing to build it up, but let's define it formally now. So let f be a function with derivatives of all orders throughout some interval containing a as an interior point. So then the Taylor series generated by f at x equals a is given by this formula here. I've got the sum from k equals 0 to infinity of f, the kth derivative of f over k factorial times x minus a to the k. And we can write it in its expanded form as we were just doing. So we have a summation notation way to write this, and then we have its expanded form. Okay, cool. And the Maclaurin series is just a Taylor series, except it's at x equals 0. So what I mean is instead of having an a here, now I'm just going to have a 0, but it's literally the same thing. So I have the kth derivative of 0 over k factorial times x to the k. So since my a is equal to 0, this is no longer x minus a, this is just x to the k. So it's actually a lot simpler. And so when x equals 0, it's just called the Maclaurin series, but we actually kind of use them interchangeably. So I could call this Maclaurin series. If I call it Maclaurin series, then you know that my a equals 0. Or I could say the Taylor series at generated by x equals 0, and that means it's a Maclaurin series. We kind of go back and forth. I see them stated in both ways. So to summarize, because this is something that I've recently found confuses the people. So Maclaurin series. Maclaurin series, so don't think that this is like some extra special thing. This is just a special type of Taylor series, but in this case, just a equals 0. So the second you say Maclaurin series, it just means a equals 0. So since Maclaurin series is a type of Taylor series, sometimes we still call it a Taylor series. We kind of interchange between the two. It's a Taylor series at x equals 0, or it's a Maclaurin series. Tomato, tomato, potato, potato. Okay, got it, good. Okay, so the first thing that you've got to do is you've got to just get used to the form of this Taylor series. And I know it looks super overwhelming when you first see it, but there is actually like a pretty clear pattern to these. And so the first thing that we've got to do is we've just got to get used to like generating a handful of these and seeing how they are built and kind of figuring out what that pattern is, so it's not quite so overwhelming. And then eventually we will do much cooler things with them, but for right now this is where we got to go. So we're going to start by finding the Taylor series generated by f of x equals 1 over x at x equals 2. So I'm just going to rewrite this as f of x equals x to the negative 1, and now we're going to find just a whole bunch of derivatives. So I just want enough derivatives, like it's just going to depend how many you need, but when you're first getting started, you're probably going to want to take a good handful. So in my case, I'm going to take 4 derivatives just so I can like really clearly start to see the pattern emerge with the derivatives. So sometimes it's going to be obvious what the pattern is, and then sometimes it's not. So it's just kind of, luck of the draw. So I start by taking a bunch of derivatives. So my first derivative is negative x to the negative second. Second derivative is 2x to the negative third. Third derivative is negative 2 times 3x to the negative fourth. And then the fourth derivative will be 2 times 3 times 4x to the negative fifth. Now, a word to the wise. I also want you just to notice like how I built these derivatives. It's not so much that I care what the number is. I'm really trying to establish the pattern. So if I had written this as -6, in the context of a Taylor series, that might not be as meaningful as seeing what the pattern is, right? Because now I can see, oh, with each successive derivative, right, I'm multiplying by whatever this is. You know, you can like start to see this like pattern emerging. And the other thing that's really good with this, right, is you can see, okay, now that I'm looking at this, my odd derivatives are negative and my even derivatives are positive. So you kind of just want to write out like what is actually going on, not necessarily just knowing, oh, what's the final number. So now that I have all of these written out, I can establish a formula for the nth derivative. So you really just need enough derivatives so that you can confidently come up with a formula for your nth derivative to start. And so in this case, so you have to just also figure out like, okay, so remember, it's negative when I have an odd derivative number, so first derivative, third derivative, so on and so forth. So for that to happen, this needs to be -1 to the n. So that means when n equals 1, right, this will be negative. When n equals 2, this will be positive. So that's the direction that I want to go. And then I have n factorial. And so this is always going, this exponent here is always one more than wherever this factorial starts. And this is always a negative exponent. So for some people, this can be a harder part of coming up with a Taylor series. And so you can also go back and like test this, right? So if I plug in n equals 1, so I'll have -x to the -2, I can see. And if I plug in n equals 2, this becomes positive. So this becomes 2x to the -3rd. So like you can also test whatever your formula is. You get better at this over time. So like the first few times you do this, just do whatever you need to prove it to yourself. Take that extra time. Once you kind of start to get that pattern recognition, this will get a little bit easier, but I know this can be a little overwhelming at first. Okay, so now we use these with our formula, our Taylor series formula, and we use our x equals 2. Remember, it's being generated by x equals 2. So in general, for some Taylor series generated by x equals a, I'm going to use this formula here. And so you can see here, I have all my derivatives, and now I can see what I need to do with them, right? Is I need to plug in my a, which is 2 in this case. And then also I need to have x minus 2's kind of running all over in the formula. So at this point now, it's just kind of plugging everything in. So just to make it clear, doing this with x equals 2, I'm going to take f of 2, f prime of 2 times x minus 2, f double prime of 2 over 2 factorial x minus 2 squared, f triple prime of 2 over 3 factorial x minus 2 to the 3rd, and I can continue this pattern on all the way out to the nth derivative as we have set up. And take your time with this the first few times you do this. Eventually, this does get a lot faster and you will see this all, but like you have to put in that investment in your brain to understand how everything connects. So like write out all that detail and really get your hands into it. So I am now going to plug in that 2 into all of my formulas. So my 1 over x becomes 1 over 2. This becomes minus 1 over 2 squared. This is 2 factorial over 2 cubed times 1 over 2 factorial. So you can now take all those pieces that we have and see how they all kind of connect. And in setting up all of these pieces, so like take your time to make sure that you've tied out all the pieces of this formula. You will very likely have to pause the video to wrap your head around where all of these pieces came from. They all come from what you see here. So I have f prime of 2, f double prime of 2 over 2 factorial. All these pieces are now in here, but it will very often take your brain just a moment to kind of connect it. So put in that investment. And once you are there and you see where all these pieces come from, you're going to notice another thing that we can do, which is actually all these factorials actually end up canceling out. And so now that all these factorials end up canceling out, I can rewrite this entire formula as what you see here. So I actually didn't even need those factorials. And so this is the other thing that happens with Taylor series is a lot of times there is a pattern to how things cancel out, and there's kind of a greater formula to how this Taylor series is built. And so that's why it's very important, like this step here, that you kind of see all the pieces that go into it so that you can generalize that formula. And so now I can totally rewrite this formula, this part here. I can like restate this formula. The more interesting thing now, or the next part of this, the other very important question, right? This is an extension of a power series, right? So my question is, does this formula here, is this going to converge? And so now we'll look at what we really have here, right? So I've got this x minus whatever to the nth, right? And I've got this negative here, but all of this is over a power of 2. And so what does that ultimately remind us of? Well, that feels a lot like a geometric series, right? Where my r is going to be related to that 1 over 2 power. And so if it's a geometric series, then the one thing I know about a geometric series, right, is that I can actually figure out where a geometric series converges. I've got this nice little formula here for a geometric series. The only difference is that now, instead of having, so when we did geometric series before, right, we just had like a bunch of numbers that we plugged in. And when I look at this, this now has numbers and variables. Okay, so let's apply this logic looking at this whole formula here. So I want to just make sure that I'm looking at this right. So I can really factor out 1/2 from each one of these, right? So that 1/2 is going to be part of my geometric series. There's kind of two different ways to look at this. So I guess what I'm trying to say is, so my a in this case is equal to 1/2 because I start with this 1/2 term. And then my r is going to be equal to, if you look at this, so now I've got x minus 2 over 2, x minus 2 over 2. These are all being squared, right? So this whole thing is being squared. And here, if I bring out this 1 over 2, I've got this whole thing to the nth power. So my r in this case is negative x minus 2 over 2. So this is what my r is going to be. So now technically as a geometric series, I can now say whether this converges or not, right? This will converge as long as my x minus 2 over 2, if this is less than 1, then I know that this series will converge because I know a whole bunch of things about geometric series. So I can be a little bit more specific about this. If this condition has to hold, this will hold as long as x minus 2 is less than 2, so I can multiply 2 to the other side. And then since this is just an absolute value inequality, I can set up this inequality here, so negative 2 is less than x minus 2 is less than 2, and then I can just solve for x. So this series will converge when x is between 0 and 4. Okay, cool. So I've got the answer to that part there, and that's not the whole picture. So I want to go back to what this sum is. And this is actually what's kind of cool with a geometric, or sorry, with a Taylor series. So my Taylor series ultimately acts like a pseudo-geometric series, right? So I plug in my a, I plug in my r, here's everything plugged in. So, I gotta do some algebra here. So I'll multiply the top and bottom here by 2 over 2. So I'm left with 1 over 2 plus x minus 2 when all is said and done. And then I can just add everything up. All of this ultimately equals 1 over x. Okay, so this is actually kind of cute. I don't know, maybe cute is the word. I'm going to call it cute. So I'm told that that whole long Taylor series that I just came up with, it sums to 1 over x. Isn't that the function that we started with? So that makes total sense. So what this means is I can take the function 1 over x, and it's kind of a surprising and very strange result, right? But ultimately, I can take that whole long series that I just wrote out, i.e. this series here. I can rewrite this, and I know now, like by that sum, that this actually does equal my original function. So one thing you have to ask yourself is, why would I want to do this? Right? Why would I want to do this? Well, there are some interesting results. There are some interesting things that happen in being able to take a function like this and rewrite it in series form and to know that they are equivalent to one another. So again, it's one of those things where that's a bigger question that we're going to have to think about as we kind of move through the material. But right now we do for sure know, right, that these two things are equal to one another, and we're just going to have to stay curious as to why might I want to use this. Okay, so let me add on to this now. So we're going to talk about then an extension of this. So I'm going to let f be a function with derivatives of order k for k equals 0 through n in some interval containing a as an integer point. So then for any little n between 0 through big N, I get these Taylor polynomials of order little n generated by f at x equals a. This will be the polynomial p sub n of x equals f of a. So notice now what's happening here. So p sub n of x equals my Taylor series. Please note what the last term is. So this is going to be a polynomial using all of those Taylor series terms. But now instead of this being an infinite series, a Taylor polynomial ends at the nth power, whatever you deem that to be. Okay, so this is now another kind of interesting thing to actually think about. Why would I ever want to have these Taylor polynomials? What could possibly be done with this? Okay, well, let's think about that for a different Taylor series. So let's find the Taylor polynomials of orders 0, 1, 2, and 3 for f of x equals 1 over x plus 1 and x equals 0. So this would be a Maclaurin series, right? Okay, so what I want you to do in this case is, I'll kind of get this started with you. So we know that the first thing that we're going to have to do, right, is if I have to find these Taylor polynomials, I'm going to have to go through the third derivative. So I'm going to view my f of x as x plus 1 to the negative 1, and then I can find that my first derivative is negative x plus 1 to the negative second. So why don't you go ahead and find the next two derivatives, and after you do that, plug in x equals 0 into all of those derivatives. So just start there. That'll kind of get you in the right space, and then hit play when you're ready. Okay, so I find my second derivative and my third derivative. And in this case, yes, I did actually just write out, what the coefficient here is. So finding a Taylor polynomial is a slightly different exercise than having to find a formula for like an infinite series. So in this case, I feel okay with just having these coefficients in front here. I'm not trying to like establish this like bigger pattern necessarily. And then I just need to plug in 0 into all of these just so I can start to see kind of what we've got. Okay, so from here, we're going to use the formula that I've got written out here. And I want to take this piece by piece just to make sure that you're seeing where all the kind of pieces are coming from. So for our first Taylor polynomial, so that's going to be the p sub 0 polynomial. So that's just going to be this first term. So that's just going to be whatever my f of a is. Now in this case, my f of a is 0, so it's just going to be f of 0. So my first Taylor polynomial is just 1. And then for my p sub 1 polynomial, so now I'm going to go out to the first derivative. So I have f of a plus f prime of a times x minus a. So in this case, since my a equals 0, I need to take whatever f of 0 is plus f prime of 0 times x minus 0. So this is what I need to plug in. And so when I plug all of that in, what I'm going to get in this case is going to be 1 plus negative 1 times x minus 0. So this is just going to simplify to 1 minus x. Okay, so now moving on to the p sub 2. So for p sub 2, so notice that that's going to take me out to the everything having a 2, like so to the everything's being squared in this term. So here's kind of the layout, but remember I need to plug in 0 for everything. So plugging in what I have for my zeros, so I have 1 minus x, those are the first two terms. Now the new term is going to be 2 over 2 factorial times x minus 0 squared. So this will simplify to 1 minus x plus x squared. And then if we move on to the p sub 3 polynomial, so now I'm going to take this out to where I get to that third exponent. And if I plug everything in, so I'm going to have 1 minus x plus 2 over 2 factorial x squared minus 6 over 3 factorial x cubed. So this is 1 minus x plus x squared minus x cubed. Okay, so now we can actually see a pretty clear pattern emerging. And I think it's kind of fun to now compare this to what's actually going on with the graph. So let's take a short field trip. So what's cool about these Taylor polynomials is actually how they approximate functions. But what does that really mean? So I have the function that we're using, 1 over x plus 1. So that's in this dotted black line. So your first Taylor polynomials, remember our first one was just 1. Not interesting, doesn't show us anything cool. But when we move to like 1 minus x, so I just want you to notice, okay, so now it's like kind of running, it touches the graph, right, at this like brief moment. Interesting. But these get more interesting as you add on more and more terms. So for instance, if I have our now p sub 2, 1 minus x plus x squared, so now you can see how for a small period of time, this function is approximating the 1 over 1 plus, or 1 over x plus 1. And so if I continue on, so now here's out to that p sub 3 that we found. So we already found this one. And so now if I continue on, so I can see the pattern pretty clearly at this point. So as I continue to kind of move through these different polynomials, what you'll notice, right, is so now if I go to the 5th term, you'll notice, so now it's just approximating just a little bit more of that original, that 1 over x plus 1 as we move along. So if I now go down to the x to the 6th term, so again, it's getting to be a better and better approximation. And I thought just for extra funsies, I would take this out. Let's see, where did I take this? I took this out to the 14th term. So I just continued the pattern out to the 14th term. So look at how good now this is kind of approximating our original function. So this is the interesting thing that Taylor polynomials will do for us. And the more terms that we add on, the closer we're going to get to this function. And so you can see, right, so at the 14th term, we're doing a okay job kind of approximating this function. And if you had an infinite amount of these terms, then you would get a polynomial that literally represents this function here if we had an infinite amount of them. Okay, so we're going to do just a few other classic Taylor series and polynomials just to make sure that we've covered them. I know this is a longer video, but I do want to kind of get through all this depth and make sure you have a solid base. So the next thing that we're going to do is we're going to find the Taylor series and Taylor polynomials generated by f of x equals e to the x. Okay, so I want to just run through this again. So the great thing about f of x equals e to the x is actually right away, right, we already know what all the derivatives look like, right? So all of the derivatives have this form f, the nth derivative is always e to the x. And then if I plug in 0, this always just equals 1. So this is actually a pretty easy Taylor series to generate. So what I would recommend actually is, so I've already kind of told you part of the pieces of this. Can you finish writing out what the Taylor series should look like? I'll give you a moment to do so. Hit play when you're ready. Okay, so I'm using my Taylor series formula here, just trying to get it in my head, right? So I'm going to have all my terms, and don't forget the factorials. So this is everything that I'm going to plug in. But all of these f primes of 0, f sub n prime of 0, these are all 1, right? So this particular Taylor series then is just 1 plus x over 2, or x squared over 2 factorial, x to the n over n factorial. So this entire series can just be written as x to the k over k factorial. So this is a classic Taylor series. It's pretty easy to generate. It's pretty quick to come up with. Okay, so the Taylor polynomial then, in general, is just going to be this form. And so I have the nth term, and it just ends at x sub n over n factorial. So you could have a Taylor series, which you would ultimately want to write in series notation, or you could have a general Taylor polynomial, and then you would want to end it at the nth term. So that is the difference between those two things, and this will be a really common thing that you do when you are working through your homework. Okay, so let's do one more. Another really classic one here is cosine of x at x equals 0. Okay, so in this case, we do know that the derivatives eventually cycle, and so you're going to actually see a pretty clear pattern emerge as you plug in x equals 0. So the first challenge that I'd like to make to you is for you to take a handful of derivatives until you establish the pattern and plug 0 into all of them and see if you can come up with a formula for the nth term at x equals 0. Okay, so I'm going to go ahead and show you. So I go ahead and I take all my derivatives. The first derivative is negative sine, second derivative is negative cosine, third derivative is sine, and then we cycle back at the fourth derivative to get to cosine of x. So if I just plug in 0 into all of these, so f of 0 is 1, f prime of 0 is 0, f double prime of 0 is negative 1, f triple prime is going to be 0, and then the fourth derivative is back to 1. So really what's going on then in this Taylor series or Taylor polynomial, right, is we're just bouncing from 1 and negative 1 at all of the even powers of n, right? So that is now going to influence what our formula is going to look like. So my general derivatives, if I have an odd derivative, so you can always represent an odd number with 2n plus 1. So all of the odd derivatives of 0 are just going to equal 0. And all of the even ones are going to equal negative 1 to the nth. Now, the tricky part with this, right, is, so this is how you represent an even number. And then you just want to make sure that you've got this set so that the pattern is correct. So if I plug in 0, right, that's going to be the first term. So at 0, this will be positive 1. And then at the second derivative, so this will be 2, n will equal 1, and so then this will equal negative 1. And that's the pattern that I need to have, right? So the first term needs to be 1, the next term needs to be negative 1. So that sets everything correctly. And this I know can be a little bit confusing, but you will start to kind of get used to the nuance of choosing these things as you work through your homework. You get a lot better at this as you kind of go through. Okay, so anyways, so now I'm using my formula. And so a lot of this particular formula drops out, right? Because all of the odd derivatives are just equal to 0. So when I set this up, so if I just plug in everything, so I've got 1, 0x, x squared over 2 factorial, and then 0x cubed, so on and so forth. So I've got this whole formula here. This really comes out to negative 1 to the 2n over 2n factorial. Oh, sorry, I meant negative 1 to the n, not 2n. So here is everything that we just kind of discussed, right? And so you can take that moment, right, to see how all the terms are kind of dropping out, or you can just kind of rest on, oh, I know that they're going to drop out. So I can then rewrite this whole series as just having the even terms like we see here. And I can write this in this series form. And so then if I wanted to get this into the Taylor polynomial form, so remember then I just have the last term in this case. This does have a last term. It is the nth term. So this would be the Taylor polynomial versus the Taylor series. So again, that's the difference between the two. Okay, so I think that's plenty. That's a lot of information, but you kind of have to see all of it together. So I'm going to leave it there, and I will talk to you guys in another video. Bye.